continue. So we have Endri Bezati, and he's a senior researcher at Computing Systems Laboratory at Huawei Zurich Research Center. His research focuses on modeling computations as stream-based data flow programs for heterogeneous computing on embedded systems and HPC. So his talk is going to be on actor transition systems and related to the graph partitioning. Yeah, please go ahead.
Yeah, okay. Thank you for the introduction. So let's start with the overview of this paper. So the idea here is to take inference graphs from PyTorch and then model it to data flow model computation called actor transition system. And I will describe the properties of this model, like the first one. Yeah. The first one that you see here is like hierarchical composition of, so an actor can have other actors inside. I will talk about how those computational units, the actors, they execute, how they are partitioned, and then how it's executed. And I will finalize the talk on how to represent now an inference network into that model. So what is actor transition system? So we represent on this model the computation as actors. So those are never-ending computations, so they execute always. They all execute in parallel. They connect with each other through first in, first out buffer communication, and they act on a stream of data, right? So because all of them they execute in parallel, already we have something that is implicit on this model. It's pipeline parallelism, right? So we have a stream of data, and the first actor here then will consume one data, it will give it to another one, and then it can already execute the other batch of data. So inside of those actors, we define actions, so what the actor is acting on, and also the actors, they have a state, so they have a permanent state, it stays. So once the program has finished, then the state is being destroyed. Okay. So I will start here with some simple examples of the Cal programming language, which is a formal way of describing the actor transition system programmatically. So here on this example, you see a very simple actor. I have omitted the types. So this actor is called add. It has two ports, A and B, and it has an output port out. So it defines a single action. And this action tells us that I will read a data from port A, another data from port B, and I will output the addition on it, right? So every time that you have two new data on its port, it's going to output the data. So because the actor transition system is based on data flow firing, on this model, it has like three additional properties. So one of those is the state, so it has a state, and you can define it in color state like this one, S0, and this state is going to be updated by the input of the actor, and it outputs the summary. So every time that we have a new value, we are outputting the summary, right? And we update also the state of the actor. The second addition of it is we can define multiple actions, and those actions, they can be guarded by predicates. So in this case, we have the first action is going to be executed if P of A is true, and in the other case, if P of A is false. Very simplistic. And the last part of it is that you can give priorities on your actions, right? So that means that once the data is available on port A, the actor actually will say, first I will see if I can execute action A, and then I will try to execute action B. Okay? So we have this kind of three properties. If you heard the discussion of Edward Lee this morning, those are deterministic actors. But we can also represent non-deterministic actors, right? So, for example, like if you want to do like asynchronous training with it, probably this way of representing the actors can help you to do it. Right? So now I talked about like some properties of this model, but I haven't talked about how actually you execute those things. Right? So as I said, that all of them they execute in parallel, right? And the job of the actor is first to select which action is going to execute that action, and then go back again, right? So it has like kind of this loop in it. And the way there are multiple ways of actually how to define an action selection. So for this work, I'm using a machine representation of the actor execution, which is called actor machine. There is a difference on the paper of it, if you are interested in it. And to execute, for example, like this multiplication actor, which is very similar to the oh, no, there is no add operation here, it should be multiply. It's okay. To execute this multiplication actor, we have three conditions. So the first condition is availability on port A. The second one is availability on port B. And the third one, which is not a necessity in the model by itself, but here we do it because we want to minimize the buffer length. I'll talk a little bit about that later. We have also the condition on the output port. So now the things that we would like to construct something that will do those checks, right? And this something looks like that. So it's kind of like a machine with different instructions. And on that machine, we define on the circuits here the state, and the state actually encapsulate the values of which conditions have been checked or not. The diamonds are the conditions, so condition instruction, which will basically check the availability or on tokens on the input and the space on the output. And we have the execution instruction that will execute basically this addition. And we have the wait instruction that the machine tells that I'm waiting. So let's assume now that I am on this state 11x. So this state defines that condition A and condition B are true, but I haven't tested yet if I have space on the output. So I'm on this state, and now I'm testing it, right? And if it's false, then I'm going to this wait instruction. So here the wait instruction tells that I cannot do anything right now, so I will just need to wait, right? And an event should come actually to activate it back again. So now let's say like this event happened, right? We go back again to that state. So basically, this means that I have remembered actually what I have checked. And I'm not going to recheck again all these conditions. So now it's true, and it will execute the action, so the operation to inside. And at the end, it will restart its execution. So there are multiple ways of constructing actually those graphs or those actor machines. So depending on what you want to have, actually, like if you want to play with latency on it, you have different configurations. So this is it's called like a single instruction actor machine. There are other representations, like we can also make like non-determined state machines out of it. You can read that on the references. So and the way that you can represent that, let's say like for software, would be like a switch case, for example. Right? So we have states. The actions can be functions. The conditions can be functions, and also the execution of the action here can be also functional. So so this paper is based on Streamblocks. So Streamblocks it's an open source compiler, and it has been developed by me and other people at EPFL. And this compiler supports the ATS model. It uses Cal as its programming language. It supports the actor machine, so it generates actor machines. It uses the RunTime, which I'm going to present next, and it gives you source code generation. So it does software, which this talk is about, but also you can also do high-level synthesis. So the runtime, right? So the thing is that if you have a lot of factors, but you don't have enough resources into it, you will need to find kind of solutions on how to attribute actors into different processing elements, and then you need to kind of schedule them. And this is actually the attributing actors to different processing elements is called partitioning. And the way that you need to schedule them in a way that you are not breaking actually the model properties. So for an actor to be executed in ARP runtime, first an actor should be mapped into a processing element. And then the actor is being selected by scheduler. I'm going to represent actually those. I'm going to say what those runs are here. This actor is going to be selected, and then we have the actor machine that does the selection of it, and it tries to execute something, an action. If an action or a lot of actions that have been checked on the actor cannot be executed, then it gives back the hand to the scheduler. So on every processing element, we have like a single thread running on it, and this thread has 3 steps: pre-fire, fire, and post-fire. Here I'm using the same terminology as in Ptolemy. It's another Edwards tool, and it has an additional termination. So on the pre-fire step, assuming that we have a lot of factors and they have been mapped into different processing elements, the pre-fire step will check how many inputs we get on this, let's say, like attributed 3 actors here, 2 actors and 4 actors here. It will see, it observes its queues. It says that I have this enough space. Okay, great. I have that amount of data. I will go now to the fire step. So the fire step is basically a non-preemptive round-robin scheduler, and non-preemptive in this sense means that if I have this actor here and I have a lot of data and I can actually execute all this data, I will execute it multiple times, right? And we can on the runtime actually we can say to it how many times we want to have this non-preemptiveness. So then we execute the actors like one by one, and if we cannot execute any more one of those, because if let's say like I have like internal actors that they communicate inside this partition, so that means I will do another round of it. So if I don't have any more, I will go to post-fire. I will update. I will signal to the other processing elements. You have data now. You can do something. And on the termination phase, we are doing 2 things. First, we check actually if the execution has finished, and this can be done like if you have like a source node or a source actor on your program that has an infinite amount of data, the program will never finish. But if you have a finite amount of data, then on the runtime, this is represented as you have an actor, it has done its job, right? So everybody has done its jobs. They will go to sleep. And if everybody is on sleep, then the runtime actually will recheck independently for each processing element. It will do another turn of the firing. And if, again, all of them are to sleep, so they cannot progress anymore, the program will terminate. And another part of it is that we can do kind of like possible deadlock detection. Right? So possible because it depends actually if you are missing space on the output. So here we do 2 kinds of deadlocks. So the one is that we check actually if an actor can execute but it doesn't have space, then the actor will trigger to its main thread that I cannot progress on that particular condition, which can be, for example, can be availability of space. And if all of them are asleep and this condition is still there, so if it goes back and it's executed and I find the same condition, then this is a possible deadlock. But now if the condition is like a predicate, so one of the guards that I was showing on the previous examples, then that means this is a deadlock caused due to bug action that have got. Okay, so so for the partitioning. So as I said, we do partitioning if we have more actors than we have processing elements. But also sometimes you can do partitioning even if you have less actors than processing elements. Probably it's better to do partitioning because you will have a lot of data traversing every partition, every processing element. So probably you limit the communication between cores, right? It depends actually a lot what you are trying to implement. So for this project, I'm using two off-the-shelf partitioning tools. The first one is called Metis, and all of them both of them they are like multi-level K-way partitioners. And on Metis you have also the possibility to have multiple constraints, and those constraints are being given like on these two parts here. So we can give actor weights and connection weights. And particularly for Metis, you take now the application graph, so how the actors are being connected. You construct an undirected graph, and then you color that graph with, for the nodes, the actor weight. And those actor weights can be kind of like abstract in a sense, like for example, like how many statements you have executed during an execution, or the map operations of an operator or of an ML operator, for example. You can either use platform profiling, and the RunTime has for processors, it has profiling. You can enable profiling already, but also you can give like memory construction. So for the connection, you give the data type and the number of tokens that they have been traversed. So the profiling happens in this way. So you compile down the program, you execute it with an input, you get all the available executions, you do the sum, and then you do the sum of the weights and the sum of the tokens that have been traversed, and then you color the graphs. For Pato, the difference is that we construct a hypergraph out of it, right? For both partitionings, we are not touching the options. So this is like the default options on the tools. Those are generic partitioning tools, and for the reason why I'm using it here, it's more like an exploration. I just want to see actually what happens with those. At EPFL, we also have like more domain-specific partitions. But in the 4 pages paper, I mean, you cannot write everything, right? So once you have partitioned your data flow application with the profiling tools, then you have a file like this one. So it's an XML format, which will define the name of the network, and you have those partitions. So in those partitions, you define an ID and actually the number of instantiated actors for that partition. So here we have two partitions, so it's split on two. And the ID here basically defines on which core those actors are pinned. So here are pinned on 0, and the other one are pinned on 1. And also, you can define the buffer size of it, right? So this file is being given at runtime to it, right? So you compile it down once, and then you give this file for testing a possible partition. Just a note on the buffer sizes. So ATS as a model, it can be synchronous, but also it can be asynchronous. Right? And normally you cannot bound the buffers on dynamic data. So, but we have solutions, available open source solutions that will, depending on input stimulus, we can find buffers that will never deadlock your system. So that's possible. So for Streambox, so the Streambox compiler will take the cal files, so the cal actors, and the representation of the network. It can take an initial partitioning if we want, Then we create the actor machines, as I showed you. So this will define the execution of our actors, and these are it's an intermediate representation actually on it. Then for this intermediate representation, we generate code. In this case, it's C++ and some scripts actually for compiling it. And then we do the compilation of the program, and then we link it with art, so our runtime, and also we can link it with torch for retrieving its operators. Right? So libtorch is a C++ library. Right? So PyTorch is based on libtorch. Once we have this, once we do the compilation, we'll have an executable, and then you can launch it with the profiling information. You get the profiling information on how many times these actors have been executed and the sum of the total the outer counters and how many times have been executed. And then we give it to the two partitioners. The partitioners will just provide the configuration files, and then we test it. So this is kind of like the compilation chain of from cal to executable plus profiling. And now on my last part of the talk, I need to go a little faster. So how now we do this transition from PyTorch to cal? So we start by taking an inference model, and then we use a project that now it's inside of PyTorch.o. It's called FunTorch, which basically will create a stateless function of the model. And now you have like a torchfix object on it, representing all the operators and their connectivity. So it will give basically DAG. And then from that DAG, we visit them and we take all the functions of the A10 functions, so the operation functions that we have been called. We route them to actors, and then we create a single forward DAG representing the inference, or multiple ones, and I explain what I mean by multiple ones. And we have another network interconnecting the reading of a tensor string, feeding to the forward one, and then a sourcing for representing the execution or checking the difference. Right? And we generate cal out of it. So I will just go super quickly on that. Basically, on the torchfix, you have the placeholders, which are basically the input tensors, the weight of your inference. The different operators are as A10 functions, and you have the output, which basically can be the output tensor of the inputs. Right? So basically, from the torchfix, you get this kind of like multiple lines of code functions. So you get the name of the function and what are the arguments of the function, and we do this kind of translation into cal. So the external keyword here means like call a function from the library. And so we detect which one are tensors and which are one just like arrays and integers and integrals, right? So we do like a one-to-one translation of the types into cal types. So once we have created this external function, then we can create an actor out of this one. And basically, for example, like a convolution actor will look like that. You have a name, you have like an input. So this convolution has two weights, that it's called. And the weights here are becoming state variable, like constant state variable. And in the end, we just do the compilation, so the convolution. If we have data on our input, then we will do this convolution, right? Simple. So one other thing that we can do is that because we are working on a stream of data, right? We have two possible ways. So if we have, let's say, like just from the input tensor, the forward graph into the output tensor, then this is the representation of one of what actually PyTorch will execute. So the boxes here, they are actors of the A10 operator. One other way to do it is like if we have like bigger batch sizes, then we can split them on small batch sizes, and instantiate multiple forward passes, right? So by basically increasing the parallelism of the system. If you don't want to split the batch size, yeah, okay. If you don't want to split the batch size, basically you can also have like if imagine that this is one here, and you have a stream of data, you just dispatch them to the different ones, right? So you have multiple ways of doing data parallelism in this case, but also you can do, say, like task parallelism on different data. So so our initial exploration, we tested on a Kumpen processor. So it's a server machine, so it has like 48 cores, 4 sockets. So in total 192 cores. It has 8 NUMA domains, I think. And first we tested the vanilla PyTorch, right? So this is this point represents the execution at 48 cores. And this is kind of like the best result that I got out of PyTorch 2. And for a single request, right? So you don't do a stream, right? Single request. And in our results, so we have like 8 different configurations. So this one is that we don't have any data parallelism, so we have just one forward graph. On 2 we have 2, 3, and 4, right? So what we observe here is that once we partition the graph, first of all we have kind of linear students, and specifically for the DP1 here with both Metis and Pato, so H is the Pato partition. You will go, you will have kind of almost like a flat line here, right? So the partitioner kind of cannot create more partitions based on because we don't have so many operators, right? But now because we are adding more parallelism, we see actually that we can get further, right? So so this is actually a very motivating result, and this actually shows that if you do streaming, so you have a stream of data, if you do streaming, you can gain a lot by using stream-based actors. Thank you. So as a conclusion, so this is like an initial exploration on it. So you use like different, we use the model, we use the actor machine, we use the art, and then we use PyTorch on it. The fine codistant checking, so on the actor machine, the latency is so small compared actually to the execution latency of the operator. And the performance is as good as actually as the partitioner can give, right? So we use, you can use Torch with it. The project is open source if you would like to try it. And we have some planified like future work for doing distributed execution training and also how to integrate art on PyTorch. That's it.
Interesting talk on combining data flow models and neural networks.
Yeah.
So I guess we have time for one question. Yeah.
Yeah, thanks. So I was wondering, like, in what part did you need the extension to ATS? Like, it seems like
no ATS. So the extension is the extension to data flow defined. Right?
Yeah, I know. So, but
in here.
Yeah.
So in here, normally you don't need.
Exactly.
Right. Okay. You don't need. But if you want to do training, so the interesting part of representing like that.
So the extension is that you allow for actors to have multiple actions.
You have multiple actions.
Predicated.
Actions. For example, like the split actor uses multiple actions. You can make it to use multiple actions because
it's just a forwarding.
Depends. They have different properties. Okay.
So, but here, and because I was wondering if you have multiple actions and predicated things, you lose static scalability, which you would get in a normal neural network, right?
Yeah, but we don't do static scaling.
But static scaling would you remove the need for calling and stuff. You could merge stuff.
So the reason why I'm not doing static scaling is because, like, imagine that you're in case of distributed execution, so you don't know actually if the data will be there, right? So this is why static scaling doesn't work on that. Right? And this is actually why the actor machine provides us this selection.
Okay, thanks a lot.
Thank you.